2.4, right? But it looks a lot like section 2.2. Today we're going to talk about applications of second order constant coefficient homogeneous ODEs, right? That's a lot of words, right? A lot of words. All of that stuff just means this one equation, right? Yeah. Second order, well, I guess maybe I should make this guy point at that, right? Second order constant coefficient homogeneous ODEs. We're going to look at a particular application of those in section 2.4. There's several applications there that you can feel free to read as much as you want and get some more details. So before we do that, we're first going to recap section 2.2. Why? Well, because it's all the same thing, right? So let's remember, what did we discover? Finally, right, we understand why all of these things are true. And what are these things? If we have a second order constant coefficient ODE, we make this assumption for our solution. That turns the ODE into an algebraic equation, which is the characteristic equation for the roots of a quadratic polynomial, which we can always write in this nice quadratic formula. And then depending on whether the b squared minus 4ac is positive, 0, or negative, that changes the nature of the actual solutions that come out, right? In case 1, we had positive, you get 2 distinct real roots, and so you get 2 solutions, and the general solution is c1 e to the r1x plus c2 e to the r2x, right? When we have 0 for b squared minus 4ac, then we have a double root, just a single root, r1. What is r1, right? r1 is just negative b over 2a, right? Okay, because that piece would be 0, yeah? And the solution is c1, the general solution is c1 e to the r1x plus c2x e to the r1x, and we learned that from our reduction of order to discover our second solution, right? And then the third case, when we have this quantity negative, we get complex conjugate roots, alpha plus and minus I beta, whatever those guys turn out to be when you're solving, right? This is alpha, and beta is going to be that with the negative sign, so they get to the square root, right? So we have these solutions then, and we went through a lot of work to see why these guys are our solutions, that each one of these pieces is the real and imaginary part of a complex valued solution that we got by using Euler's formula to look at our complex valued solution. And the solution is c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. So we've got solutions, right? That's pretty cool, right? We've got solutions in all cases. So what is one of the applications that we're going to do? And that's for a mechanical mass spring system. For a mechanical mass spring system with no external forcing, okay? That's what we're going to look at. We'll later derive this equation. We will later derive. Right now, we're just going to write it down. We will later derive when we do some more with this a little bit later. So we'll later derive that the governing equation is, okay, you ready, you ready, you ready? M y double prime plus b y prime plus k y is equal to 0. Ooh, okay, well that looks kind of good if we just know something about what m, what b and k are, right? So let's see, what's the idea here? the idea here is I meant to bring an actual spring system so I could show you, but you basically kind of have some something that a spring is attached to, okay? And then you have a mass, right, on that spring, and you pull down, so the mass has there's an equilibrium position where it will just rest, but if we pull down on it or push up on it, then it will start to oscillate back and forth, right? Okay? So, what are these things M, B, and K? They must be some type of physical related parameters, yeah? Okay, so let's talk about that. Well, first of all, what is Y, right? So, our dependent variable here, Y, I'm using Y because I'm looking at it in this vertical direction. It's nice in the book. It looks at it in the horizontal direction too. Either way is fine. And then we're using X, right? So, you know, you just read your dependent variable from the equation, and then we're generally thinking of time as the independent variable when you're thinking about this physical scenario, right? So Y of t is our unknown function here, and so t is now our independent variable instead of x, and this is our displacement from equilibrium. Displacement from equilibrium. Right, so this level right here would be y equals 0, right? Okay? So y of t is telling you displacement from equilibrium at any time t. Okay? So what is m? You might guess, right? Good, m is the mass of the object. Okay, so that's the mass of our object. At the end of the spring, an example of a unit might be kilograms. Maybe I'll just get that EG out of there so you don't think of that. An example of the unit might be kilograms, okay, for measuring mass. What is B? B is a friction coefficient. Now, unfortunately, your book uses C for the friction coefficient. I'm not going to use C because I don't want you to get it confused with this, so I'm going to also use B, okay, for lots of books will use B, some will use F. Anyway, so I'm not going to use C, so be careful of that, okay? So B is a friction coefficient, and what is K? K is a spring constant. Associated with the stiffness of the spring, okay? Friction is kind of like whether you might have like a damping agent in here as well, like something resisting the motion. If you have an old-fashioned screen door on your front door or something like that, there's little dampers there that resist the motion, okay? Okay, so let's talk a little bit about this for a sec. This is also called the damping coefficient for that same reason I just talked about. And let's talk a minute about units, right? Let's talk a minute about units. Okay, so let's think about this, right? What are the units? This is M, mass, right? That's kilograms, right? Y double prime, if Y is displacement, let's say measured in meters. For example, meters, okay? So if we measure displacement in meters, then what's Y double prime measured in? Well, what are we going to measure time in? Let's say, so displacement is meters at time t, let's say seconds. Oops, sorry. T units, seconds. Okay? What's Y double prime measured in? Good. Meters per second squared. So the units of this term is kilogram meters per second squared. What is that? Good. Newton, right? A Newton is a kilogram meter per second squared. Okay? And so what do we know? That's a unit of force, right? So this equation is coming from a force balance. All right, very nice. Okay. What would y prime be measured in? Good. Meters per second. Yeah? Okay, well then what does b have to be measured in? Everything has to have the same units, right? So this coefficient of friction has to have units of what? Good. Kilograms per second, right? Because then together they're kilogram meters per second squared. Yes? Okay? And then what is y measured in? Y is measured in meters. So tell me, what is k measured in? Good. Kilograms per second squared, right? And that way we have units that all match across our equation, right? In the book, they'll give you those units in newtons, right? Related to newtons, you should make sure that you get that they're all the same thing, okay? What else do we know, right? M is the mass of an object. It's going to be positive, right? K, our spring constant, is going to be positive. And B, our damping coefficient, is going to be positive or 0, right? So if B is equal to 0, we have no damping. And if B is positive, we have damping. Okay? All right. Let's see. And this equation also requires the spring to satisfy Hooke's law, which is a linear law, and therefore why we're getting out a nice constant coefficient, ODE. All right. So, well, what do we have, right? We've got an equation that looks a lot like this, yeah? Okay, and so we know that we've got these sets of solutions, but actually we now have like 4 different cases we want to think about, okay? So let's come back here to our equation, right? We're going to analyze that equation. So we're going to analyze, right? Now, my double prime plus by prime, see, it's another reason not to change it, plus ky equals 0, right? And what are we going to get? Well, mr squared plus br plus k is equal to 0. And the characteristic equation is then going to have a 2m down here, right? And a b squared minus 4mk there, right? Okay? Awesome. And it's the exact same thing, except for now we'd be doing y is e to the rt, because t is our independent variable, and that's what would have resulted in this, yeah? And so let's look at our cases, okay? So we're really actually going to have 4 cases we want to think about, okay? 4 cases we want to think about. So our first case is going to be this guy, which is going to be b squared minus 4mk positive, right? So same deal, b squared minus 4mk is positive. Then what are we going to get out? 2 real roots, right? That distinct roots that are not equal. These are going to be t's, yeah? Okay? So can we say anything now about just creating some more space here for myself? Can we say anything about this solution? Okay, so what did we just say that we know here? We know that in this case, right, so we'll start with 3 cases. So we're going to have 4 total cases. Our first 3 cases are going to be positive. Okay, so these cases all involve damping. Okay, We're not going to let b be equal to 0. In our fourth case will be when b is 0. We'll come back to that. Okay? So for all of these guys, we're going to think about b being positive. Okay. Well, if that's the case, right, and if b squared minus 4mk is positive, right? So that guy's positive, so I'm going to put that over here, right? B squared minus 4mk is positive. Yeah, that's the case one we're in, okay? Well, I know m and k are positive, right? These two guys are positive, so I'm taking something away from b squared, yeah? So b squared minus something positive is smaller than b squared. Yes, do you agree? Awesome. Okay, and then if I take the square root, since this is a nice inequality and I have is greater than 0, I can take the square root, and that would say that the square root of b squared minus 4mk is less than b, right? Remember, b is positive. And so if this expression right here, right, this square root is smaller than b, and b is positive, so I'm going to have negative b plus something smaller than b. That root is going to be negative, so R1 will be negative, and then I'll have minus b minus something positive, and so that root will be negative. And so not only do we get that in the case of the physical example, that we have two real roots that aren't equal, but they are both negative, okay? For the reasons we just walked through. Well, what does that then mean, right? If we think about what if we're interested in long-term behavior, what's going to happen with this spring mass system, right? So spring mass systems are kind of, you engineers know, right? They're sort of behind how you think about all kinds of different things, right? You would like to know what's going to happen in the long run without having to go through a whole lot. And so what is going to happen in the long run it's nice we have our solutions right here. And so let's take the limit, right, as t goes to infinity of y of t for this equation, right? That would be the limit as t goes to infinity of some constant e to the r1t plus some other constant e to the r2t, where I know that both of these constants are negative. So these are exponential decays, right? And what is going to happen to this limit with exponential decay? Right? Good. I've got exponential decay. So that guy's going to 0. Yeah? Okay? Because these guys are negative. Okay? So I know that my spring mass system will eventually settle back in to its equilibrium value, right? To its equilibrium starting point. All right. That's super cool. We call that overdamping. This is called overdamping. Why is it overdamped? Well, there's no oscillation that's happening, okay? No oscillation in the spring. It doesn't go back and forth, right? Well, you can see that from the solutions. It's exponentials, right? Exponentials don't oscillate. And so, it moves. How do you start it off? You either give it some initial displacement, that's your y at x naught, or y at t naught, right? Or you give it or you could push it up for initial displacement, right? That's your first initial condition. Your other initial condition is you could just hit it, right? You could have some initial velocity, okay? Or push it down, okay? So your initial position, your initial velocity are what start it moving, and then it does its thing until it gets back to equilibrium. In case 1, if you have this relationship between the coefficient of friction, the mass, and the spring constant, then you won't oscillate at all. You'll just go back very quickly to equilibrium. Does that make sense? That's called overdamped. Okay? So let's look at the next case. Okay? What's the next case then? This one. Okay? So case 2 here, if b squared minus 4ac, well, it's not ac anymore, right? It's b squared minus 4mk. If that's 0, then what are we going to have? e to the r, c1 e to the r1t, c1, now this will be a t, right? That's the independent variable, yeah? So t e to the r1t, yeah? r1 is a real number, r1 is a double root, right? What is r1? We just said r1 is minus b over 2m because this quantity is 0, right? B and m are positive, and therefore this is also negative, right? Does that make sense? And so if that expression is negative, then the question becomes, oh good, I'm just going to be able to edit this, right? What is the limit as t goes to infinity of y of t? And that's the limit as t goes to infinity of c1 e to the r1t plus c2 t e to the r1t, right? Where r1 is negative, right? Okay? Well, this guy's clearly exponential decay, but what happens here, right? T's going to infinity. This is going to 0. Infinity times 0 is an indeterminate form, right? But what do you know? This guy is negative. You can think about him down at the bottom, and then he's positive. T over e to a positive exponential. Think about calculus, right? Who wins as t goes to infinity, exponentials or polynomials? Exponentials, right? So this guy wins out, even though t's going to infinity, this is driving to 0, and the limit is 0, right? And therefore, again, we decay exponentially, okay? But not quite as fast, because this guy tries to kick in for a little bit to fight the battle, but against an exponential decay, he's got no hope, right? That case is called critically damped. I'll just write that here. That's critically damped. It's this one transition instant between this case and this case, right? Okay? For an actual spring to legit satisfy b squared minus 4mk equals 0 identically, that would be pretty unusual, okay? So it's kind of the critical transition point between overdamped and what this guy is called. Any guesses? Underdamped. I'm glad I wrote this one over that one, right? Hey, that one's overdamped, that one's underdamped. Haha. Anyway, so let's see what's happening with underdamped, right? Okay. So now what do we have? B squared minus 4mk is negative, right? What are our solutions? C1 e to the alpha t cosine beta t plus C2 e to the alpha t. This is so great, right? Minus sine beta t. R is alpha plus and minus I beta. Still, we have complex conjugate roots. Yeah. Now I'm just going to create more space for myself. I guess, well, I'll go ahead and erase it. Okay, so what's happening there now? Okay, so if we're thinking about taking a limit as t goes to infinity of y of t, we're talking about a limit as t goes to infinity of c1. Now, for a specific initial value problem, you would have determined c1 and c2 to be specific numbers, okay? E to the alpha t cosine beta t plus c2 e to the alpha t sine beta t, right? So what do we know that cosine and sine do as t goes to infinity, right? They just oscillate back and forth forever, right? So what about this guy alpha? What is alpha, right? That's with the exponential piece. What is alpha? Well, if I've got complex conjugate roots, right? This part is going to be alpha, right? Okay? And beta is going to be 4mk minus b squared divided by 2m, right? Because beta is real, yeah? Which is You'd have to swap them, yeah? You would just solve it, you wouldn't be plugging into a formula. But anyway, so what is alpha, right? Alpha in our complex conjugate root case, alpha is negative b over 2m, right? So if I write that there, negative b over 2m, right? T, in fact, we could do that, right, with R1 as well, right? Okay, in this case, right, negative b over 2m, negative b over 2m, yeah? Okay, it's b and m are positive, it's more clear that that's exponential decay. Same thing here, minus b over 2m t, yeah? And so even though sine and cosine both oscillate forever, right, between what? Negative 1 and 1 as t goes to infinity, multiplying them by an exponential function that has exponential decay is going to drive both of those guys to 0, right? Okay? These would be like a nice use of pinching theorem from calculus, right? Remember that fun stuff? Sandwich theorem, squeeze theorem, pinching theorem, all those things. Okay, so what do we got? This limit is also 0, okay? So in all three of these cases, overdamped, critically damped, and underdamped, the spring max system eventually just returns to its equilibrium position. So you did something to get it started, and then eventually it just goes back, okay? Okay. You could think about like bridge construction, you know, and you might think it's bad for things to oscillate, or maybe it's good for things to oscillate a little bit with forces, and then, but you do want them to settle out to their equilibrium position in the end, right? So let's look at this for a sec. What is happening here? It'll be a decaying exponential, right? Or I mean a decaying sign, kind of thing like that. Yeah, you can look at some better pictures in your book, right? A decaying oscillation or wave, yeah, right? And then if you think about this, yeah, I'll just pretend that goes the whole way up. You can look in your book for better pictures. That goes the whole way down. Okay. So these curves, they should look like this. Sorry. Anyway, you can look in your book for better pictures. These curves are the envelope. Right, those curves are the envelope of the oscillation, and they're giving you your max and min, like how far you're at any time you're possibly going to oscillate with whatever your spring mass system is trying to model, right? So the envelope is pretty important, right? And what is the envelope going to be? It's going to be your bounds, right? The max and the min of this expression, and that's just going to be some constant times e to the minus b over 2m t, right? Because of the nature of cosine and sine, and you're bouncing between minus 1 and 1, and this bottom one will be minus that. So that's kind of important to give you at any time t just how far away things can move before they eventually head, right, to equilibrium, right? So what I'm graphing here is displacement from your equilibrium. Like this was equilibrium. Yeah? There's some cool programs and things that we'll look at later visually once we're back in class, and it's super easy to just pull up fun things on the internet and show them, unlike right now. Okay, so let's now go look at our case 4. Yeah? Okay? Super cool, we're all good? Life is happy? Yay, okay. Okay, so in case 4, right, we're gonna have b is 0, and case 4 is going to be the undamped case. okay? So there's no oscillation in this one, in overdamped, there's no oscillation in critically damped, right? There is an oscillation with underdamped because it's not damped enough to damp out the oscillation, right, for at first, but then eventually it gets damped. Yes, does that make sense? Okay. All right, so now let's go look at undamped. Well, obviously, right, if B is 0, then we don't have that, and we don't have that, right? And so this is your R, yeah? So this is one way to do it, if B is 0. And so what do we have? R is plus or minus. Well, that's the same as the square root of 4 times the square root of -1 times the square root of m times k. Yes, that top piece. And the bottom is 2m. What's the square root of 4? Good, 2. Yeah. Okay, so those 2's cancel. What's the square root of -1? I. So we have the square root of m. We'll write it like this, the square root of m times the square root of k all over m times I plus or minus. Yeah? But the square root of m over m is just 1 over the square root of m, and so what is R? The square root of k over m plus or minus the square root of k over m I. Now, you wouldn't really plug into that. What you would do instead is that the undamped equation looks like this, right? Just erase that. All right? The undamped equation, B is 0, and so what do we get for our quadratic equation? We get that, and so therefore m times r squared plus k is 0, so r squared is minus k over m, right? So what is r? Plus or minus the square root of minus k over m, but k and m are both positive, so k divided by m is positive, so r is plus or minus the square root of k over m I, right? So what do we have? Instead of, we have complex conjugate roots, but they are purely imaginary roots, right? Purely imaginary. There's no real part. Right? No real part. That means alpha is what? Good. 0, right? Oh, okay, I guess I still want that up there. Alpha is 0, and what is beta? Beta is the square root of k over m, right? Yeah? Awesome. So, let's erase that. I'm going to erase that. That's going to be awesome. I'm going to replace this guy with alpha. Right? So, here's our general solution in any case of complex conjugate roots. Those are still complex conjugate roots, right? But they're purely imaginary, so this is the general solution. So we're going to plug in alpha equals 0, right? And beta equals square root k over m. So what will we get? C1 e to the 0t cosine of square root k over m t plus C2 e to the 0t sine of square root k over m t, right? Well, what's e to the 0t? Good, that's 1, right? So what do we get? Y of t is C1 cosine square root k over m t plus C2 sine square root k over m. And now what do we have? A pure oscillation, right? Cosine and sine just off, but can you tell me what the limit as t goes to infinity of y of t now? does not exist, right? Because sine and cosine just oscillate back and forth forever. Awesome. Okay, so with this purely a math, so we have oscillation forever. Spring never settles back to its equilibrium position. This is called, you guys know it? You engineers know it? It's a hint. Simple harmonic motion. Okay? Simple harmonic motion is going to come from an equation, an ODE, a constant times y double prime plus a constant times y is 0. And we've seen this equation before, right? If we divide through by m, we get y double prime and move that guy to the other side is equal to minus k over my, right? Okay? Remember, back in chapter 1, we looked at solutions of y double prime is equal to minus some constant squared times y, right? Okay? And we saw the solutions of that were sines and cosines, right? Okay, t. Yeah, so it's the same idea, right? This is also simple harmonic motion, simple harmonic motion. Here, this k is not that k, right? Okay. So here's the equation. What's the idea? You've got purely imaginary roots, and we have motion that oscillates forever. With some trig identities, always your favorite thing, right? You can show that this is equivalent to y as a function of t is some other constant times cosine of the square root of k over m t minus gamma, okay? Make sure there's nothing else I didn't want to mention. What is everything? Where omega naught, curly looking w, omega, subscript 0 naught, right? That's square root of k over m. You'll see that notation in the book. This guy is called the angular frequency. Okay, it's measured in radians per time. So it's more of a natural frequency. For a problem like this, right? As opposed to regular frequency, which is just measured in cycles per time, okay? Per time, has units of per time. This guy is radians per time. Our constant C here, which is the amplitude of our wave, right? So basically it's just, right? The amplitude of the simple harmonic motion wave is, you can show is C1 squared plus C2 squared. Hopefully you kind of get a sense of where that's coming from. Obviously it's the amplitude of the cosine wave, right? Cosine goes between -1 and 1. So this version is kind of nice. This one's much nicer to work with as far as like differential equations and solving things, systems for the initial conditions and thinking about a variety of things. But this one is nice because you just are working with this single cosine wave. Okay, that's the amplitude, and then the tangent of gamma is C2 over C1, and gamma is called the phase shift, right? And it is exactly what you would expect. What's the left to right shift of the phase of the wave, okay? So that's it for today. There's lots more examples and there's examples with specific numbers and specific scenarios in your book. I'll let you read those because I think you're tired of my long videos. And there's other examples related to other scenarios. We'll be revisiting some of this once we learn something about non-homogeneous equations, and that's when we'll derive the model. See you soon.